Hi, in this chapter we are going to talk about the so-called knapsack problem. So let's get started. What is the knapsack problem? It is a problem in combinatorial optimization. Given a set of items, each with a mass W and a value V, and determine the number of each item to include in a collection so that the total weight M is less than or equal to a given limit and the total value as large as possible. So the problem often arises in resource allocation where there are financial constraints. It has lots of applications. For example, finding the least wasteful way to cut raw materials, contest of investments and portfolios, seating contest of assets for asset-backed securitization, constructing and scoring of tests in which the test takers have a choice as to which questions they answer. So as you say, there are lots of application. So this algorithm is among the others that definitely worth understanding and to know how to implement it efficiently. So there are two knapsack problems. I mean that there's a divisible problem. If we can take fractions of the given items, then the greedy approach can be used. The so-called 0-1 knapsack problem, we can take fractions. We have to decide whether we take a given item or not. But the divisible knapsack problem, we can take fractions of the given item, and the greedy approach can be used. The greedy algorithm is the following. We have to sort the items according to their values. It can be done in ordo n log n time complexity, for example with the help of quicksort or with the help of merge sort. There are lots of, or for example heap sort is very efficient. There are lots of algorithms out there that can perform this running time. And we have to start with the item that is the most valuable and take as much as possible. So I think this is the naive approach. We want to take as much as we can from the items that's worth the most, and then try with the next item from our sorted list. As far as this linear probing is concerned, it can be done in linear time complexity. So the overall complexity of this greedy approach in order to solve the divisible knapsack problem has ordo n log n time complexity, which is not so bad. So we can solve the divisible knapsack problem quite fast. But it's not the case in the 0-1 problem. In this case, we are not able to take fractions. We have to decide whether to take an item or not. And the greedy algorithm will not provide the optimal result and solution. Another approach would be to sort by cost per unit weight and include from highest on down until knapsack is full, but it is not a good solution too, because in the greedy section, in the divisible problem, we sorted according to the values of the items. This approach would be to sort according to cost per unit weight. So it would be a bit different, but it is not a good approach too. So we have to use dynamic programming. It is the right way. So what is dynamic programming in a few words? Solves larger problem by relating it to overlapping subproblems and then solves the subproblems itself. A typical dynamic programming practice is to solve the Fibonacci numbers, because if you know what are the Fibonacci numbers, then there are a lot of subproblems and a lot of calculation that we keep doing again and again. So one of the main points in dynamic programming is try to avoid these overall recalculations. It works through the exponential set of solutions, but doesn't examine them all explicitly, and stores intermediate results so that they aren't recomputed. This is what we call memoization. And the solution to original problem is easily computed from the solutions to the subproblems, and that's what we are going to do during the implementation of our 0-1 knapsack problem. So knapsack with dynamic programming, we have to define subproblems. We have n items, so we have to make n decisions whether to take the item with the given index or not. So the subproblems, the solution considering every possible combination of remaining items and remaining weight. So we are going to define a so-called knapsack table. In this case, I denote this knapsack table with S. We are going to see the illustration with a concrete example. I think it will be clear. And the solution to the subproblem corresponding to the I items and available weight V, or in other words, I think it's a bit better that SIV, it is a two-dimensional array, the maximum cost of items that fit inside a knapsack of size or weight W, choosing from the first I items. So this is a typical approach that, for example, we have n items, but we make subproblems. So in the beginning, we try to solve the problem for just one item, then for two items, then for three items, and then step by step, we come to the conclusion how to solve the problem for general n items. So we have to decide whether to take the I item or not. And this is the typical equation we are after. So in the knapsack table, it's a two-dimensional array, as I said earlier. We have to decide, and this is the root of our subproblem, that we have to choose between taking and not taking the ith item. If we take the ith item, we end up with Si-1 W with the given indices. And the other side, we took the item, so we get the value. This is what Vi stands for. Plus, we have to update the knapsack the knapsack table. So these equations will be very, very important. But we are only considering Si-1 V minus Vi if it can fit inside our knapsack, because have a maximum capacity for knapsack, and we can't take any more items. So if there is no room for it, the answer is just Si-1 W. So I think these equations there's no point in talking about it without a concrete problem and without solving a concrete problem, because I think it's not so understandable. So I'm going to talk a bit about the time complexity, and in the next video we are going to see a concrete problem. We are going to solve this knapsack table and help with this maximization subproblem equation, and later on we are going to implement our knapsack problem step by step together. So as far as the time complexity is concerned, the running time of the knapsack is ordo n times W, where n is the number of items and W is the maximum capacity of the knapsack. But it is not polynomial, it is pseudo-polynomial. And the numeric algorithm runs in pseudo-polynomial time if its running time is polynomial in the numeric value of the input, but it is exponential in the length of the input, so the number of bits required to represent it. We are going to see that we come to the conclusion that the running time of knapsack is ordo n times 3. It's very easy because we are going to have a for loop, and inside the for loop there is another for loop, so there will be nested for loops. So we come to the conclusion that the time complexity is something like this. And I think that in the next video we are going to talk about give an example. Thanks for watching.